Alright, Module 2, Lesson 11. Hopefully I will be able to get through this. We have been sequencing basic rigid motions to show that they were the same. The exact same size and the same shape, and that's called congruence. So we're going to talk a little bit more about congruence in topic C. So you have seen something like this where it said translation of S equals S prime, or reflection or rotation. So now we're going to talk about congruence. So if we have congruence of S equals S prime, all that means is that S, so this means S is congruent to S prime. And we can write that with a symbol. The symbol for congruent is this. It's an equal sign with a little squiggly line over it. So we could say S is congruent to S prime. So this statement up here, okay, right here, is the same as this statement right here. Okay, so they're just congruent to one another. And so what we're going to do is we're going to work on demonstrating that basic rigid motions, or a sequence of basic rigid motions, shows congruency. So we're going to start with these two triangles. Okay, we have triangle ABC and triangle A prime, B prime, C prime. Now, in the triangle, we have these little arc marks. Okay, this arc mark, there's one arc mark at B, and there's one arc mark at B prime. That just shows that those two angles are the same angle measure. Okay, and when there are two arc marks at C and two arc marks at C prime, that shows that they're the same angle measure. Okay, so what we're going to do is we're going to describe a sequence of rigid motions that shows this, and we're going to be very, very detailed, like we were in 9 and 10. I think we were detailed in sequence of rigid motions. So I'm going to draw this first one. Okay, I'm going to trace triangle ABC. And the first thing I want you guys to start doing is connecting one of the points from the original figure to another point. And to connect them, you would do a translation. Okay, and for me, it's easier if I translate on the outside, like B to B prime. So I would do like this, a vector, B to B prime, and then I'd move it like that. Okay, so to write that out, okay, that would be translate, I can do it up here. Translate triangle ABC along vector B, B prime. And then it would be here. Okay? Then the next thing I would do is I just need to move this part down here. So it would just be a rotation around B prime, and because I went clockwise, it would be negative D degrees. So then I would rotate triangle ABC around B prime, negative D degrees, and I just want to match up C to C prime. So then it would look like this. Everyone good with that? Okay, so that's how you would be very specific in your descriptions here. Okay. So because of this, because they match up exactly where the arc marks are, and the arc marks are down here, then we can say that triangle ABC is congruent to triangle A prime, B prime, C prime. Okay, so this right here proves congruency, because when we translate and rotate, it keeps the same angle measures and it keeps the same segment lengths. So the sides are still the same length and the angle measures are still the same measure. So that's how we prove that it's congruent. Okay? So instead of saying that they're the same size and the same shape now, we're going to say that they are congruent. And because they're congruent, they are also similar. Okay? That's how we do that. Okay? So let's look at it this way. So once I move this here, if I have this shape and I've already translated it and reflected it, right, we know that S is congruent to S prime. Now the question is, S prime congruent to S? I would assume that you would tell me yes. Okay, so S prime, you would say, is congruent to S because S was congruent to S prime. Okay, but we have to do a little bit of work to prove that they are congruent. Okay, so if I did this, we can see this. So then we would just have to undo it. And we talked about undoing things in our last one. So if we reflect it, flip it over, they line up, and then do along the vector, they line up. So this shows that they are congruent. So if you go one way, you can undo it, and then they are congruent. Okay? So what we're going to do is we can say that a sequence of rigid motions proves congruence, just like we did up here. Okay, and we can undo it to prove congruence. Okay, so then we could go backwards. We could rotate it and then translate it and get it back to this location. Okay, so what we're going to do is we're going to hop right into this. Okay, we're going to work through this a little bit. It says, describe a sequence of rigid motions that shows that S1 is congruent to S2. Okay, so we're looking at S1 is right here, and S2 is right here. So, you would take your transparency, and you would kind of just work through and figure out how to make them congruent. Obviously, when I talk about these, I've told you guys several times that I would connect them first. So, I'm going to make a point here and a point here. And I'm going to call this A, and I'm going to call this B. That way it's easier for me to describe it when I translate it so that they're connected. Okay? So, you would trace your first one. And some of you may be able to do this without tracing it, and that is completely okay. And some people may need to trace it. Okay? So, I would first trace it, and then I'm going to draw my vector AB right here. And then draw it on here as well. And then I would translate it along vector AB. That would be my first thing. Then I would rotate it around point B, negative D degrees, so that it lines up. And then once I've rotated it then I would reflect it, flip it over, and then it would line up. So this would require all three motions. So to write this, it would say, because it says describe it to show that they're congruent, so you got to write it out. So translate S1 along vector AB. Then we rotated S1, the one that was up here, around B, negative D degrees, so that, I'm not even going to put anything, so that the sides, the long straight side lined up. And then we reflected it over, and I guess I could put a point and call that C over side BC. Okay, you can't reflect over a point, but you can reflect over a line. So if it doesn't have a line with a name on it, name it, and then use it, just like I did here. Put your own labels on it and describe it. Because if you put your own labels and describe it, and I can see what you wrote, and I can see how you labeled it and see what you wrote, then I can walk through your steps. But if you don't have 2 points to say it reflected over a line, then it's not going to be fully correct. Okay, on B, it says describe a sequence of rigid motions that shows that, is there a picture there? Yes. That S2 is congruent to S3. Okay? If you can see this visually without using the transparency, don't use the transparency. Just write it out. Okay? If you need to use the transparency, use the transparency. I'm going to use the transparency so people can visually see it, and then we'll go from there. Okay? Here we go. Oh. Don't like this one. Okay? I have my transparency, and I know I would translate it so that the points meet, just like that. I don't have any points yet, so I'm going to go ahead and do that right now. I'm going to label this X, and I'm going to label this Y, and I'm going to put a vector in there and call it vector XY. Okay? So I would take S2 and I would translate it along vector XY, just like that. Okay, can't see that very well, the green. That's better. And then I would just rotate it negative D degrees around Y. And it lines up. So this time we only needed 2. So I would translate S2 along vector XY. And then I would rotate it. Rotate S2 around Y, negative D degrees. And when I do that, okay, that proves that S2 is congruent to S3. So S2 is congruent to S3. Okay? And then on C. Describe a sequence of basic rigid motions that shows that S1 is congruent to S3. Okay, so we're going to do the same thing again, except for now we're looking at S1 and S3. Okay, so there are no points, there is no vector, so I'm going to start with that. Let me see. M and N, I don't know. You can make up those points. And I'm going to draw a vector in there because I want them to, the first thing is one of the points to at least be connected. Okay? So then if you need your transparency, okay, to kind of walk through this, use it with me. If not, you can probably go ahead and write it out if you can do it without the transparency. Sorry, I keep saying transparency. I mean sheet protector. Okay, so if we take this and move it along vector MN right here. It's so hard with this fat marker to get the whole shape. Okay, just like this. Okay, then we would rotate it. I'm going to rotate it this way so that the long straight side lines up. Okay, if you wanted to rotate it counterclockwise, that would be fine, but it just is easier when I have that straight side lined up. Okay, so then I have that straight side lined up. So I would rotate it -d degrees around N. And I need another point. I don't have a point here because I'm going to need it to reflect over. Okay. And then I would just reflect it over in O. Okay. So, this is what it would say. Translate S1 along vector MN. Then you would rotate S1 around N. I went clockwise, so that would be -d degrees. And then I would reflect S1 over segment NO. And what those three things do, it proves that S1 could land right on top of S3, but it proves that they are congruent. So the S1 is congruent to S3. And if they're congruent, they are also similar. Okay? Doing what we did in A, okay, in A, to prove that S1 was congruent to S2, and what we did in B, proving that S2 was congruent to S3, would we really have had to do this to prove that S1 was congruent to S3? No, because we know that S1 is congruent to S2 and S3 is congruent to S2, okay, we could say that S1 is congruent to S2. And we wouldn't have had to do all of this work, but it's good practice for us so that we know how to do it later. Okay, so what we need to know is that when we do a sequence of rigid motions, it proves congruence, and that if we prove congruent to the same thing, like we did here, that S1 was congruent to S2 and S3 was congruent to S2, then that these two on the outside, S1 and S3, are congruent to each other. Alright? So what we're going to do is we're going to hop on over to exercise 1, so go ahead and turn your page. Oh. Did we do exercise 1? Oh, nope. Sorry, exercise 2. So, let me back up just for a second. So when we do basic rigid motions, we know that they take a line to a line, a ray to a ray, a segment to a segment, an angle to an angle. Okay. We also know that a basic rigid motion preserves segment length and it preserves angle measures. So when we're talking about congruence, congruence also does all of those things. Congruence takes array to array, a line to, or maps a line to a line, array to array, a segment to a segment, angle to an angle. Congruence preserves an angle measure, and congruence preserves length of segments. Okay. So the same properties that were the same for reflection, rotation, translation are the same for congruence. So when we talk about congruent figures, we're talking about those same properties. Now let's look at example 2. Okay. Perform the sequence of a translation followed by a rotation figure XYZ, where T is a translation along vector AB, and R is a rotation of d degrees. You choose the degrees around O. Label the transformed figure X prime, Y prime, Z prime. And then it asks, is XYZ congruent to X prime, Y prime, Z prime? Okay, so we're going to do this sequence of rigid motions and then determine if they are congruent. Okay, so here we go. So on this one you would actually have to do it because it says perform the sequence. So you're going to have to do this one. Okay. So we're going to trace our shape, XYZ. And our vector. So if we were to do this, okay, we would just translate it along the vector just like this. So this is where XYZ would be. Everybody good with that? Okay, so now take it and put it under your paper. Line it up and draw it. And only draw the figure. Do not draw the new vector and do not label it. We do not label until we've done the entire sequence. Okay? So then we're going to take our figure back out. Okay? We're going to do our center. We're going to mark our center. And then we're going to rotate it d degrees. You choose. Okay? So you could do positive or you could do negative. It doesn't matter. And I'm going to do negative. I'm going to rotate it clockwise like this. You could rotate it as much or as little as you want. It's completely up to you. Okay? And then put it underneath and retrace it. And now is when you label it. So this would be X prime, this would be Y prime, and this would be Z prime. Okay? And the question asks, so you've done the transformation, and then it asks, is XYZ congruent to X prime, Y prime, Z prime? X, Y, Z is congruent to X prime, y prime, z prime. Okay? Because we did two rigid motions and they preserve segment length and angle measures. Okay? And that's just what our lesson summary says here. That congruence 1 maps a line to a line, array to array. So congruence maps a line to a line, array to array, segment to segment, and angle to angle. Congruence preserves length of segments, and congruence preserves angles of measure. The symbol for congruence is right here. Okay? You need to make sure that you're using these properties when it says explain. Okay? Or how do you know? Your problem set is there on S61 and 62. You can go ahead and work on that.